All right. Today we are going to be doing the notes for 110 through 113. And if anybody has any questions on this, you're going to be feel free to talk to me about it at another date. And I hope I just didn't break my elbow that I just dropped. So we're going to find out here. Okay, we did not. All right, so your homework is going to be the worksheet 111 and 113 that you're going to get in class if you haven't already gotten it. So the first assignment is there are three types of discontinuity. And by the way, all of these are about continuity. And there are three examples or three types of discontinuity. And this is one you got way back when. So we're looking at this place right here. That is called point discontinuity. And in calculus, we call that removable, and I'll explain that why later. And then this kind of continuity right here, this kind of continuity right there is called jump discontinuity. And by the way, f of c is undefined is why that one doesn't work. And then the limit as you approach c from the left and the right is not equal, so it does not exist is why that doesn't work. And then this one is called infinite discontinuity because you're going to negative infinity or positive infinity. And so this is infinite discontinuity. And both of these in the middle are called non-removable. Those are non-removable. And then the last kind of discontinuity, again, this is a hole, because as you come up here, the limits are equal, but the point is open here because the point's down here. So maybe where I should have started was there's three things that have to be true for a function to be continuous at a certain place. And in this case, we're talking about a c value. And that first thing is that f of c is defined. In other words, there is a point there, and you're going to tell what the point is when you do this. On the second step, you are going to need to do the limit as x approaches c from the left of the function. And that's going to equal some limit. And then you have to do the limit as x approaches c from the right of the function, the right of the point c, I should say, instead of the function. And that has, these two things have to be equal. And then we're going to have to state that the limit as x approaches c of the function is some L value. And by the way, up here, you're going to have f of c equals, and you're going to have some value there. And in order for this function to be continuous at this c value through here, the f of c, in other words, step one, is going to have to equal the limit as x approaches c of f of x. In other words, the answer from the point, the y value of the point, has to equal the limit from both sides. Number two, 1 and 2 have to be equal. When those three things happen, then you have a continuous function. So right here is from 2000 something. I can't read it because I cut it off up there. But this is a actual AP test question here. It's 2011, and it was the open-ended part number 6, which is a non-calculator question. So it says, let f be the function defined by this piecewise, and 99% of the time you're going to be doing piecewise, and part A was show that f is continuous at 0. So this 0 is the c that we were talking about on the other side. So you do these, you're literally going to put down step 1, and you're going to say f of 0, because we're talking about this 0. And then we got to look at which one of these to use. Because the top one has an equal sign, we're going to use the top one. So this is going to equal 1 minus 2 sine of 0. And I hope you know the sign of 0 is 0, so that is 1. And then for step 2, we are going to do the limit as x approaches 0 from the left side of this function. And left side means less than, so we're going to use this top one again. And that again is going to be 1 minus 2 sine 0 equals 1. And then we are going to do the limit as x approaches 0 from the right side of f of x. And that means from the right side of 0. So I'm going to use this one down here in the bottom. So it's going to be e to the -4 times 0, which is e to the 0. And I hope we all know anything to the 0 power is 1. So since the limit from the left and limit from the right are equal, we get the limit as x approaches 0 for this function f of x is equal to 1. And in step 3, we're going to say that f of 0 from the first one is equal to the limit as x approaches 0 for the second function. And I like putting on the end, they're both 1. So that, because all three of those things we talked about on the previous page are true, that makes this thing a function. This at 0, this piecewise function is a function, or is continuous. You may recall, in our case, it would be from pre-calculus, that discontinuities fall into 2 categories. Now, you probably didn't talk about this in pre-calculus, but we just talked about on the other side. And those 2 types are removable, which is point discontinuity, and non-removable. And that is going to be the other 2 kinds, jump discontinuity and infinite discontinuity. So the 2 types, this one's got 2 blanks, so this one's the non-removable. I'm going to abbreviate because of space, and their graphic description is jump discontinuity, this thing. And the other one is, I don't have infinite in here. We call it infinite here. He must call it asymptotic, although he didn't spell that right. And we put asymptote. It's because it is an asymptote, which we call infinite discontinuity. Here, that's where you have a vertical asymptote like this one in this picture down here. And then the removable kind is when you have a hole. And we're going to do some examples of those now. All right. So if you look right here, this is an example right here of jump discontinuity, because you're going along a graph and you have to jump down here to stay on it. This thing right here is infinite discontinuity, because you have an asymptote and this graph's going up forever and ever on each side, and we'll never hit that point. So that's infinite discontinuity, and these 2 are non-removable. And then we have a hole here and we have a hole here. Either one of those are holes, so they're both examples. So it says the graph above is f of x. Determine all x values where f of x is not continue and classify as removable or non-removable. So f of x is discontinuous at x equals -1 and x equals 1, because, I'm going to put a b/ for because, and you can do that too, because non-removable. And discontinuous at x equals 3 and x equals 5, and where there are holes, they are removable. I probably should have put removable in here, removable discontinuity. And I probably should have put non-removable discontinuity here. It would have made more sense. Going on to the last section, we're going to actually do some of these problems. It says list x values where g of x is not continuous and classify each type of discontinuity. So what we want to do here is we want to factor this thing to see if we can remove anything. So I'm going to take and factor the top part, and we get x plus 8 and x minus 5. And then we're going to do the bottom part, which is going to factor to x plus 2 and x minus 5. So if you look at this, this is why it's called removable, because these reduce out. Now, I hope you remember that whatever makes the denominator 0 can't happen. So we need to say x is, or x, I'm sorry, f of x has, let's call it that way. F of x has removable discontinuity at x equals 5, because that's where x minus 5 would be 0. And when they reduce out, if you recall from Algebra 2 and pre-calculus, that made a hole. And then we would say f of x has non-removable discontinuity at x equals -2, because we can't get rid of that x and negative x plus 2 there. -2 makes this 0. See, it's removable because we reduce those out. That leaves us the fraction x plus 8 over x plus 2. We could not get rid of the x plus 2. We remove this, but there's still a hole there. And that's basically the end of that problem. It's just asking us to tell where that thing is discontinuous. So we are going to, oh, we're also supposed to have almost left that off. Right intervals for where the function is continuous. So this graph is continuous from -infinity. And now we want to find which one of these we come to first, which is -2 on the number line. So f of x continuous on from -infinity to -2, and then we put a u here for union because we got to jump over -2. So whatever we had there, we jump over because -2 doesn't work, and parentheses means it doesn't work. And then it's going to work up to 5 because that's the next discontinuous. And we have to jump over 5, and then 5 goes on to infinity. So this is the intervals on which this graph is continuous. We jumped over -2 and jumped over 5. Parentheses means it's not included, and we always put parentheses at -infinity, infinity, because you can never reach those. Part 3 says consider the piecewise defined function of h of x down here below. We got 4 pieces there. I haven't seen that many on an AP test. Doesn't mean they won't do that though. Determine all x values where h of x is discontinuous and classify each as removable or non-removable. So what we want to do here is we want to do our steps for continuity. So if you look, there's a possible discontinuity at -2. There's another possible discontinuity at 1. And then the last possible discontinuity is at 3. So we got a lot of work here to do. We need to do all 3 of these in order to find out where the discontinuity is. So we want to first find out, is there a value at f of -2? Well, do you see there's an equal sign here? Since that equal sign's there, means we can plug -2 in right here, which is going to be -2 squared minus 9, which is 4 minus 9, which gives me -5. And then we want to do the limit as x approaches -2 from the left of this function. I'm just going to abbreviate f to save some time on writing, and that's left is less than. So I got to plug -2 in here. So 2 times -2 minus 1. 2 times -2 minus 1 is -5. And then we do the limit from the right, which is the same as the top one of the f function, which again is going to be -5. So the limit as x approaches 2 of f of x equals 5. And this is step 2 I should have put here. And then step 3, if you look up there, f of -2 does equal the limit as x approaches 2 of f of x at -5. So that means this function is continuous at x equals 2. And then we have to check the next one. So when we check the next one, we are going to do f of 1. So I'm going to do it right here. I'm going to put f of 1. Now I look for the equal sign in these two things. I'm going to erase my circles. So if you look, this one here at the bottom has the equal sign. So I got to put 3 times 1 plus 2 is going to equal, let's see, that's 5. So that's step 1. So f of 1 does exist. It is defined. 2, I'm going to do the limit as x approaches 1 from the left side of this. And you know what? I put f's all over here. That's really wrong. It should be h's. I screwed up because I forgot that was an h of x right there. They will not count that wrong on the AP test because that's something everybody five. So we just found out that the limit as x approaches 1 of h of x does not exist. So this is jump discontinuity because you're going to two different y values right here. Oops, sorry, right here, these two on the limits. So that would be jump discontinuity. They go to different places. So that is non-removable. So we have non-removable discontinuity at x equals 1. That's one of our answers. And now we got to check 3 here. Well, if you look at step 1 for 3, you do f of 3. There's no equal sign. So that means this is undefined. Now we should do the limit to find out if it is a whole or if it is a, it is already definitely not continuous at 3. But we're going to check to see if it's a whole, because if the limit is there, then it's going to be a whole. If the limit does not exist, then it'll be jump again. So we're going to do the limit as x approaches 3 from the left side, and I put f up here again, and that still should be h, my bad. So 3 from the left side, there's the less than for this. We plug 3 in there, and we get 3 times 3 plus 2 is 11. And we do the limit from the right side of h, which is this bottom one, and we get 4 times 3 minus 1, which is 11. So that means the limit exists there. In other words, you go to the same value on both those. So the limit does exist there, but we're undefined here. So that's going to make a whole. So we would say this is removable discontinuity at x equals 3. So these are the two answers, and all that work I did is how you prove those things. Last problem, and we're going to be done here. This piecewise function is k of x. So I hope I remember to put k instead of f. Find values for a and b that make k of x continuous everywhere. Be sure the definition of continuity and demonstrate proper notation. Now, this problem is pretty challenging, and it takes time because we got a lot of work to do because we got to worry about it at 2s, and we got to worry about continuity at 3s. So first thing, as always, well, what I would do first is I would do this thing right here. I would do this factors to x plus 2 and x minus 2. Okay, and then this x minus 2 and that x minus 2 reduce. So this whole thing right here equals x plus 2. But we have a whole at 2. We have a whole at 2, but that thing reduces to x plus 2. So I'm only going to be worried about x plus 2. So I'm going to do step 1, and I'm going to say f of 2. Well, 2 equals 2 here. You see it? There's an equal sign, so we're going to use this one, and we're going to plug 2 in there. So 2 squared is 4, so this is going to be 4a, and 2 times b is plus 2b, and then we have a plus 3. And then step 2 says we want to get the limit from the left as we approach 2 from the left of k of x. And again, I put an f here again, even though I said don't do it. So the left one is this one. So I'm going to plug 2 in here, and that's going to be 2 plus 2, which is 4. Now, what we need to pay attention to here is we need to notice that the limit from the right is going to be this same thing right here. So that's going to give us an equation with two variables. It's going to be that 4a plus 2b plus 3. So that gives me an equation with two variables. That tells me that 4a plus 2b plus 3 equals 4, which means 4a plus 2b equals 1. So I have one equation with two variables, and I hope you remember from the good old days of algebra 1 and 2, you got to have two equations with two variables. So I'm going to skip from this one, and I'm going to start checking out the 3 values. So I'm going to do step 1 for the k of 3. And it's the equal one down here at the bottom. So when I do that, I'm going to plug 3 in for that x. So I'm going to get 6 minus a plus b. And then I got to do the limits. So I'm going to do the limit as x approaches 3 from the left side, which is this top one of k. And I'm going to plug 3 in there, and I'm going to get 9a. I'm going to plug 3 in there and get plus 3b plus 3. And then this limit here from the right is going to be the exact same one as the top one, 6 minus a plus b. Well, these two things have to be equal in order to get these to get a limit. So we need to say that 9a plus 3b plus 3 on this side, so I'm going to subtract this 3 over here with that 6, gives me a 6. So if you look, I now have two equations with two variables. So we're going to do elimination because we've done elimination before. Let's see, I'm going to check my math real quick here. I don't think I made a mistake, but maybe I did. Let's check this again. 3, 9a. Plus 3b plus 3. I don't want to have to do the video over. I'm going to plug 3 in here. I get 6 minus a plus b. Set those equal. Add a over 10. Subtract b over 2b. 3. All right, I think we're good. Okay, so I'm going to multiply this row over here by negative 1 because I can see the b should cancel. So I get negative 4a minus 2b equals negative 1. Which gives me 6a is going to equal 2. So a is going to equal 2 over 6, which is 1/3. There's my a value. Now we can take that 1/3 and we can stick that in wherever we want, into any one of these equations we want. And I think I'm going to stick it in right there. So I'm going to get 10 times 1/3 plus 2b is going to equal 3. So this is going to be 10/3 plus 2b, getting a common denominator, that would be 9/3. Multiplying that by 3 over 3. So when I subtract 10/3 over, I'm going to get negative 1/3. It's supposed to be a 1 right there. And when you divide by 2 or multiply by a half, b would be negative 1/6. So it looks like to me b is negative 1/6 and a is 1/3. So I hope I didn't make any algebra mistakes there, but if I did, we will take care of that at a different time. So I hope you have a good day, and I will see you all on Monday or Tuesday.